Hello, good afternoon, everyone. Hello, whether I'm audible to all?
Yes, sir.
Okay. So we'll start with the lab. Okay. So in today's lab, we'll see about the basic gates slash universal gates and the buffer. Okay, because yesterday we have seen about inverter, how to write the code, and how to write the test bench for that. Today we'll discuss about the universal gates and the buffer. Okay, fine. So we'll start with the basic gates. Okay, we'll start with the basic gates now. Then later we'll see, or we can start with the buffer itself. Okay, otherwise we'll start with the buffer. Yeah, so we'll start with the buffer. So you can see this is the code for the buffer. So it will start with the model, the reserved keyword, and the model name. And for buffer, we know the symbol, right? The symbol for buffer is nothing but like this, right? Where we have the input, only one input and one output. So we have a symbol like this, and we are going to find for whatever the input is there. Okay, it will be there at what output, right? So when a is equal to 0, y is equal to 0. When a is equal to 1, y is equal to 1, right? Is it correct, buffer?
Yes.
Okay, so everyone knows, right, about buffer. So buffer is nothing but whatever is there at the input will get at the output. When input is 0, output is 0. When the input is 1, the output is 1. Okay, so that is the explanation for the buffer. Then you can see the code now here. So it will start with the model name, then the model name, and in the bracket we are defining the input output, so a comma y, and we have the input a, the output register y. Why we are using a register to store the results storage. Then it depends on the input, the output depends on the input, so we have, it depends only on the input a. So we have the input here always at a. Begin, again begin if a, so means what, so yesterday I told you, if a is nothing but when a is high, when a is high the output is high, so y is equal to 1 bit 1, because we know that, so I told you when the input is high the output is high too. So y is equal to 1 bit 0, 1 bit 1. Else means what, when the input is a, if a is 0, that is nothing but else. When the input, when the input a is 0, the output is also 0, so y 1 bit 0. End, because we have begin here, so we will end that begin, then end the module, end the module. Similarly, the test bench. So you again you start with the model, then the test bench name for this, then the input. So whatever the input is there, we have to replace by a register in case of test bench. So we have register A, then wire y. The output is replaced by wire y, and the fourth line is very important, so we have to call that function the model name. So model name here we have defined, or we have written here buffer. So buffer space dot in the bracket a comma y semicolon, then initial begin, then you specify the truth table, then you just write the truth table for this, okay, for different time intervals. So it will, for the first value, the first value will start at, the first value will start at 0, second will be at 10 nanosecond, third will be at 20 nanosecond, and the fourth will be at 40 nanoseconds. So 0, 10 plus 20, 30, 30 plus 10, 40. So the last value will be at 40, that is 1. After that it will be remain constant, because again, because after this line we don't have any values, so it will remain constant, that is 1 after 40. Okay, after 40 it will remain a constant. Okay. So then end it, end mode. So this is the code, so we'll execute this and check it out. So here, so what I will do here, inside this project itself I'll create one more file, add to project new file. Okay, otherwise I will show you once again. Just go to file, close the project. Okay, close the project. So the first step is what, go to file, new project. Okay, so give the project name. So I will write lab 2, lab 2. So other settings you keep it as it is. So project name I've given as lab 2, click OK. Then you'll get this window. So in this, we have to choose create new file, create the new file, and give the file name as buffer. Okay, give the file name as buffer, and instead of Verilog, select, instead of VSTL, select Verilog, and click OK. Fine. So click on, select the create new file, then you will get this window. Then the file name you can give buffer, and the file type will be Verilog. Click OK. Then you close this window, close this window, so that you can see here on the left side and buffer.v. Okay, buffer.b you can see. So click on that to write. So to write the code, double click on this file, that is buffer.b, and just write the code. So what I will do, just copy the code from here for this. Just I'll copy it. So this is the code. I will save this, or Control S to save, or otherwise go to file and save it. Go to file and save it. Before compiling, we have to save the file. Then to compile or to check if any errors we have in the code, we can go to compile and select compile selected. Go to file, go to compile, and in that compile option, we go select compile selected. Yes. So we can see here at the bottom, at the transcript window. At the transcript window, we can see it here that compile of buffer.v was successful. So means what? We don't have any errors in the code. So it is fine to simulate the code now. So now we have to simulate the code. Okay. So to simulate the code, go to simulate, then click on, then from in the simulate, we have to select start simulation. Then from the start simulation, we have to go inside the work directory. We have to click on this plus sign. We have to go inside this work directory, and whatever the buffer, the model name we are given. What is the model name we are given here? We are given the model name as buffer. Select buffer and uncheck this enable optimization. Uncheck this enable optimization and click OK. Fine. So in the work directory, we have to select the model name. So model name is buffer, and we have to uncheck the enable optimization. Click OK. Okay, so wait for some time. So it will pop up some windows. Okay, you can see now in the instance that is simulation default, you can see the buffer file here, buffer simulation file, that is okay. So right click on this buffer file, right click, then go to add to wave all items in region. Right click on the buffer, add to wave all items in region. Select that, then you can see you will find your signals, input signal and output signal, buffer slash a and buffer slash y. You can see this. Now in case of the design file or the main code, we have to apply the clock only for the inputs. We have to apply the clock only for the inputs. So the input is here a, so right click on the input a and click on clock. Okay, click on clock, right click on the input a, click on select clock. Then you can change, if you want to change, you can change the period, or if you want to change the duty cycle, you can change the duty cycle of it. Okay, but in this case we have only one input, so I will keep the default values. I will select okay. Then finally from here I will select the run option. I will select the run option, which is beside on the right side of this 100 nanosecond. I will select this run option. Okay, click on that. So if I click once again, if I click go on clicking the run option or the run button, you can get the waveforms like this. Okay, if I click continuously, you will get the waveforms like this, right? So you can see that when the input is 0, the output is 0. When the input is 1, the output is 1, right? Are you getting it? So this is what we have defined, right? We have defined the statement for buffer. Whatever the input is there, you'll get that. You will get at the output side, right?
Yes,
Yes,
sir.
sir.
Okay. Now this is the half part. Now we have to write the test bench for this. So to write the test bench, we have to end the simulation first. Okay. So don't start writing the test bench before without terminating the simulation window. Okay. To terminate the simulation, go to simulate and click and select end simulation. In the simulation tab, we have to set the option that is end simulation. Then click on S. So you will come back to the original windows like this with the code editor, and we have the library tab and the project tab here. Okay, there are two options at the left bottom corner, that is library and project. So we have to go inside this project. We have to go inside the project, and here now here we can see here we have only one file, that is buffer, the main file, that is buffer.v. Now we have to write the test bench. To write the test bench for this, right click. Okay, right click in the project tab and add to project. Select add to project, new file, and now you give the file name as buffer underscore tb. Okay, you can give any name for this, right? You can give any name for this. I will give the name as buffer underscore tb, and again the file type is verilog. We have to change it to verilog and click OK. So you can see the buffer underscore tb file is created. To write the code, double click on this file and just try go on writing this in the blank editor. So I'll copy that code. I will copy this, fine, and I'll paste it here. Okay, so this is the code for uh, buffer, the test bench code for buffer. Okay, so save it, go to file and save the file, or in shortcut key will be Control S. Fine. So we can save the code for test bench. Then, so we have to check whether we have the errors or no. So what we have to do, we have to go to compile and compile selected. Okay, so you can see at the bottom here in the transcript window, compile of inverter underscore tb dot p was successful. Now, so it is now free of errors. Fine. Suppose if I want to do, if I do the error mistakes in the code, okay, so we can check it out what the code is, what the error we will find, we will get. So I'll compile. Then you can see compile of buffer underscore tb dot p failed with error. To find where exactly the errors are there, you can click on this message, that is compile of buffer underscore tb dot p failed with one error. Double click on that. Then you will get this window. Then it is saying that line number 5, see this message, error message, that is the location, that is D drive model tech examples buffer dot v in the bracket 5. So the bracket 5 is nothing but the line number, so it is expecting semicolon or comma. Okay, so this is how we can find the errors, where exactly the errors are there. So line number 5 means it will be above that line number 5. So it is a, we have a semicolon here, it will be a semicolon. Then save it and compile once again. Compile selected. So you can see the compile of buffer underscore tb was successful. Then we go to simulate. Same procedure again, go to simulate, start simulation. Then in this simulation, we have to go inside the work directory, and in the work directory we have to select what we have to select here now in the work directory.
Buffer underscore tb dot v.
Buffer underscore tb. Okay, only the model name we have to select here. The model name is what? Model name is buffer underscore tb. So see, we have defined in the code, that is the model name here is buffer underscore tb. So that we have to select here and click ok. Fine. So we'll get some windows, right? So you can see buffer underscore tb. Inside that we have what? A dot, that is device under test. Dot is nothing but device under test. So that is what we have written in the code, that is buffer dot in bracket a comma y, right? So again the same procedure, right click on this buffer underscore tb, right click on that buffer underscore tb, add to wave all items in region, add to wave all items in region. Then you'll get this window, right? So in this case, in case of test bench simulation, we should not apply any clock because we have already hard coded the truth table in the code. So directly we have to run this, directly run. So you can see the output. So when the input is 0, output is 0. When the input is 1, the output is 1. Again, when the input is 0, the output is 0. Again, when the input is 1, this. See this, the output, when the input after 40 nanosecond, it is constant, that is 1, because only those the values we have mentioned here in the code, right, up to 40. That is the first line here. This line will start at 0 nanosecond. The second line will start with 10 nanosecond at 10 nanosecond. The third line will start at 20 nanosecond. Then the fourth will be at that is 40. That is 0 plus 10 plus 20 plus 40, that is 10. It will be what? 40 totally. So up to that value it is defined up to 40 nanoseconds. So look at the vertical line here, it is written here 40 nanosecond. So after 40 nanosecond the value will be constant, that is 1, because we don't have any values after that, right? After this we don't have any values after this 40 nanosecond. Okay, so that is what you'll get the output for the test bench of buffer. The test bench of buffer. Are you getting it?
Yes, sir.
So we'll go with the next experiment, that is the universal gates. So in the exam, you have to show the test bench output. Okay, in the exam you have to show the test bench output, not the main code output. Okay, you have to write both the codes. Okay, first you write the main code, you check if it is working correctly or no, then you go for test bench, then you have to show the output for that test bench. Fine. So we will write, we'll see now about basic gates or the universal gates. So I will end the simulation for this. Okay. Then in the project, so in this lab 2 itself, I will create the basic gates. So I will create here add to project, new file. So the file name I will give as bg, right? Bg for basic gates. Then I will select Verilog, click OK. Fine. So in this, I will copy the code. So this is the code for your this basic gates. Okay. So basic gate means all the gates, like, so it is defined here. See, model, then the model name, input output, it is defined. The inputs are A and B. So in this case, we have two inputs. Then all the output is defined here, y1, y2 up to y7. Then the assignment. So this is this type of assignment, this type of code, it is called as what? Data flow style. Okay, whatever the code we have written, it is what? A data flow style, because we don't have any always keyword here. So if always comes in picture, it will be a behavioral description. Okay, it will be a behavioral description. So here we are writing the data flow description for this. You can write behavioral also, no issues for that. Okay, but we will use for this data flow description. Okay, so we will compile it and check the output. So I have copied that code, right? So for this, you should remember the operators. Okay, for operator, for not get, the operator is negation. For and get, the operator is ampersand. For or get, the operator is pipeline. This is the pipeline. Then for NAND gate, it will be what? Negation in the bracket A ampersand B. For NOR, it is negation in the bracket A pipe B. For XOR, A XOR B. Okay, and for XNOR, it is negation in the bracket A XOR B. So the operators you should remember. Okay, for NOR gate, AND gate, OR gate, NAND, NOR, XOR, and XNOR. So totally 7 gates we have. Fine. So we will compile it. So save it. Go to File and save or Control S. Then check if we have any errors here. Right. So I will do the error, and I'll make the mistake and find out where exactly the error is. So I have done the error here. So I have done the mistake in the code. So I'll just compile it and check where exactly there is error are there. Okay. Now see. So we are getting the message compile of bg.v failed with one error. Okay. To find the error where exactly it is, what we have to do? We have to double click on this error or the message. Then you'll get this window. So it will show the location where exactly it is there. So it is saying that line number that is bg.p in the bracket 2. So bracket 2, 2 is nothing but what? The line number. Okay, line number, and it is saying that syntax error. It is a syntax error, unexpected input, expecting semicolon. So it is saying that it is we should have semicolon in the code. So we have to go in the code, and it will be line number 2. It will be above line number 2. So there is a mistake in line number 1. So it will show at line number 2, but it will be there in line number 1. So we have to add here semicolon here to the first line, semicolon, save it and compile. Okay, so you can see now compile of bg.p was successful. And then it is now free of errors. Then we have to go to simulate and start simulation. Go to simulate, start simulation. Then in the work directory, we have to select. So what is the name for what is the name model name we have given? We have given the model name as all gates. So you can see in the work directory we have all gates. Select that and click OK. Right. Right. And now you'll see that all gets file, the model name. So right click on that, add to wave all items in region. All items in region. So you can see like this. See, and one thing you remember that when you add the signals to the waveform window, so you have to click outside first. You have to click outside first, then you assign the clocks. Okay, you have to click outside, then you assign the clocks. So I will select the input A and I will assign the clock for that. Select right click on that, on the input signal A, then you select clock, then you define the then you can, if you want, you can change the duty cycle and the period. For input A I will keep as it is. I will click OK. And for B, for the input signal B, I will right click on that, select clock, and for this now I will change the duty cycle. I will change the period of it. I will change the period of it. Instead of 100 I will make it I'll make it what, 120. Instead of 100 I will make it 120, or I will make it 85. Okay, I will make it 85 and click OK. I will change the period of signal B to 85 and click OK. So once we define the clock for the input signals A and B, we have to run the simulation part. Just we have to run the just we have to run the run option here. So we have to click on the run option and we'll get the output. Okay, so click on this. So you can see we are getting some output. Right. So now look at this. So Y1, is nothing but the NOT gate. Okay, so for NOT gate we have only one input. The input is here. Uh, the input is here what? A, that is 1. So the output is 0. Y2 is what? Y2 is nothing but an AND gate. AND gate. So for AND gate we have two inputs A and B. So A values and B values. So look at this. Look at this here. Right. Look at this. So we have the input A and B is 1 1. Then the Y2 value will be what? For input A and for input A and B, if it is 1 1, what is the output of AND gate?
1.
1, right? So this is how we can check the output. Similarly, what is Y3? What is Y3? If you see what is Y3 here, Y3 is nothing but OR gate. Okay, so Y3 is nothing but OR gate. So when for OR gate, again, for when the input is 1 1, the output is 1, right? Similarly, for Y6, what is Y6? If you find out what is Y6, Y6 is nothing but XOR. Okay, so for 1 1, what will be the output for XOR? XOR gate?
0.
0, right? Or XOR gate, when the input is 1 1, if the inputs are same, then the output will be 0. If the inputs are different, the output is 1 for XOR gate, right? Okay, so this is how we can check. So we can check for different combinations. Okay, we can check it for different combinations. So we can move the cursor. So we can get the different combinations. So look at this. If I move the cursor here, the vertical orange, that is the vertical yellow line. See now the input is 0 1. Then if I move it here, the input is 1 0. Right? If you want 0 0, again check in the waveform where the 0 0 is there, where 1 is 1 0 is there, where 1 1 is there, and where 0 1 is there. You can check in the waveforms and you can click on that and you can verify the outputs. Okay, just you have to move the this vertical line. Okay, you'll get different combinations of inputs. Right. So now we will write the test bench for this. Okay. See in the main file we are applying clock to the inputs. Okay, for the main file we are applying the clock for the inputs. For test bench we are not applying any clock. We are just running the simulation without applying the clocks. So I will write the test bench for this. So before that we have to end the simulation of it. So go to simulate, end the simulation, click S. Okay. Then, so we'll come back to the original code. This is the code. So we have different code tabs here: buffer, bg, buffer.p. So inside the project tab, right click on this, right click here in this window, add to project, new file. So now you give the new file name as bg_tb, bg_tb. Then you select Verilog and click OK. So bg_tb, click on that file. Okay, then copy the code from here. I'll copy this code from here and paste it. Right. Right. Now see the code. Again, it will start from the model name, then registers. So register for the input. So input here, there are two inputs, A and B, then wire. So here the output is not single output. We have 7 outputs. So Y1, Y2, Y3, Y4, Y5, Y6 to Y7. Then the fourth line is very important. We have to call whatever the model name we have defined the main file. So we have defined the model name in the main file as all gets. Okay, then duty, inside duty, and define the input output parameters. Then initially begin. So you can see this. If you see this, so we are defining what? The inputs. Right? From the truth table, we are defining the inputs. It will start from 0, 0, 0, 1, 1, 0, and 1, 1. Okay, so at 0 nanosecond, the input is 0, 0. At 10 nanosecond, the input is 0, 1. At 20 nanosecond, the input is 1, 0. At 40 nanosecond, the input is 1, 1. So it will start at 0, then 10, 10 plus 20, 30, 30 plus 40 will be 70. Okay, so end module. So save this file, Control S, save the file, save it, and go to check if any errors are there. So what we have to do to find if any errors are there in the code?
Error.
Hmm?
We have to run compile, sir.
Compile, right? We have to go to compile option, which is then in here at the top, at the top of the toolbar. So go to this compile, then you select compile selected. So you can see the compile of bg_tb.p was successful, right? If you get this message only, you have to simulate the code, right? So after that, go to simulate, then go to start simulation. Then in the work directory, what we have to select?
bg_tb.v.
All gets
No.
underscore tb.
Yeah.
All gets underscore tb.
Right. Or gets_tb we have to select. What is the model name that we have to select?
All needs, sorry.
Not the file name. Not the file name. Fine. We have to select whatever the model name we are given for that. So it is all gets_tb. So we have to select that and click OK. Okay. Fine. Then again you will get some windows. So you'll see that model name all gets_tb, the model name here. Then right click on that. Then select add to wave all items in region. Add to wave all items in region. Okay. Right click on the all grid_tb. Then you select add to wave all items in region. Right. Then see this. If you see here, all the inputs are selected now. If you see all the inputs and outputs are selected, so what we have to do, we have to click outside here first. You have to click outside. Okay, it should be a gray color like this. It should be a gray color like this. Now, none of the input and output is selected. If I select, it becomes white like this. Okay, you should select. You have to click outside. Then you have to run. Now this is the test bench. Now this is the test bench simulation part. So we should not apply anything the clock to the inputs A and B. We should not apply anything to the inputs A and B. Just we have to run the simulation. Okay, without giving the clock for the input A and B, just we have to run the simulation part. So click on this run button. So you can see you'll get the output. The first, so it will be the first at 0 nanosecond. So you can see it here. You can see here vertical line. It is written at the bottom here 0 nanosecond. Then I move the cursor At 10 nanosecond, what is that? It will be 0, 1 because we have defined already in the code. At 10 nanosecond, the inputs are what? 0, 1. So that is what we are getting here, 0, 1, right? The input. Then at 30 nanosecond, because 0 plus 0 plus 20, 10 plus 20 is nothing but 30. So at 30 nanosecond, the input is what? 1, 0. Then at 70 nanoseconds, okay, 70 nanosecond, the input is 1, 1. Input is 1, 1. Then you can verify the output. You can verify what for 0, 0, what are the output for NAND gate, NOR gate, XOR gate, and so on. Okay, you can verify with the input values 0, 0, 0, 1, 1, 0, and 1, 1. Okay, so if I take 1, 1, so last one is XNOR. So last one is XNOR, that is Y7. So when the input is 1, 1 for XNOR, what is the output we will get? For XNOR?
Oh, 1, sir.
1, right? For XNOR, when the input is 1, 1, the output is high, right? That is 1. So that is what we are getting by 7 here. By 7 here, you can see in this white color, by 7, the output is 1. Okay. Then for 1, 0. For 1, 0, what is XNOR value? What is the XNOR output for 1, 0? Output for XNOR 1, 0?
0.
0. So that is what we are getting here by 7. The output is 0. Are you getting it? Hello?
Yes.
Yes, sir.
Okay, so this is what about all the gates. So we have completed 3 experiments. One is inverter, one is buffer, and one is basic gates. Okay. So in tomorrow's lab, we will see about the transmission gate and some flip-flops like D flip-flop, then SR, JK, and T flip-flops. Okay. And did you install the software in your systems?
Yes, sir.
Are you
Yes, sir.
facing any are you facing any issues? If any issues are there, you let me know. I will try to find out the issues.
No issues, sir.
Okay. So is it running? The code is running.
Yes. Yes, sir.
Okay. So you practice. So whatever the programs we are executing day by day, just try to finish off in that day itself. In the same day. Okay. So yesterday we have completed inverter. Today you just try to execute these 2 codes, that is buffer and the basic hits. So the PDF I will share in today. This PDF of all the codes I will share it. Just copy and paste and just check it out. But don't but do one thing. Just don't copy paste. Just you try to type the code. Okay, because in the exam you will do the mistake while typing. So make sure that you type the code and execute. After practicing, just you can just copy and paste the code and run. Okay.
Yes, sir.
So we'll stop. I will stop it here and we'll meet tomorrow at the same time, 2:30. Fine.
Yes, sir.
We'll
Okay,
stop
sir.
it. Okay, thank you very much.
Thank you, sir.
Thank you, sir.